like one right in my neighborhood that I know. So I'm like on the edge. If I move over, I live in the middle of nowhere. Yeah. Wait.
Oh, how are we gonna get that?
I literally live in the middle of nowhere. Yeah. There's a good place.
Someone snitched on me. Or no.
Yeah, but we said.
Are we gonna get that report or not?
There's some kids.
Wait, actually? That guy is sneeze.
No, but you can just take it, put on your computer. Copy.
Oh, that's great. I'm just not here. No, so. Not here.
Wait, when you go to the library, towards the library, have that like three-way stop.
That's zero. It's not gonna change your.
Oh, yeah, I usually never get that. Yeah, I know.
She got mad. Good job. She got mad at you. You didn't have a great speed with one day. It was in the hall, you know how like she walks out of the thing and just stands there. That's what she got mad at us. Yeah, she did the same thing. Yeah, she was. Oh.
Let me finish going over page 19 with the polar area problem. So part B, we talked about how if we convert it in terms of x, we know x equals r cosine theta, we know y equals r sine theta. We can put this in the calculator and look for theta 2.4667. But if you do math 8 to get your derivative, leave it in terms of rectangular. Don't try to do it in terms of theta. I mean, it's possible, but I just think it's a little bit cleaner to just leave everything with the form that we're used to. And only go into polar mode if you're trying to graph a polar graph. Otherwise, I think doing everything in rectangular form, I think is easier. So we get dy d theta, we get the x d theta, we take those components, divide over each other, and we get our dy dx, 0.47327. For part C, particle moves along the curve r equals 1 minus 2 cosine theta. We see a bunch of d over dt notations show up. So we're going to go through our derivative process thinking in terms of related rates. So r becomes dr dt, 1 goes to 0, cosine of theta becomes negative sine theta times d theta dt. Replace theta with 2 pi over 3, replace d theta dt with 2, and then we can solve for dr dt. And dr dt is going to be 2 root 3. Now this is a positive rate. This is 2 root 3 is the rate at which the radius is changing with respect to time. So radius is increasing by 2 root 3 when t is when theta is equal to 2 pi over 3. So then when theta equals 2 pi over 3, the particle is moving away from the origin since my radius is greater than 0 and my dr dt is greater than 0 and my radius is greater than 0. So we basically are kind of tracking the movement in terms of the radius. If the radius is positive and the rate is if the rate is positive and the rate is positive, we know that radius is increasing. That means that particle is moving away from the origin. Okay, let's see if we can work through the rest of these problems one by one. So let's go to page 42. Sorry, number 42, page 20. Polar curve is given by differential function r equals f of theta. If the line tangent to the polar curve is horizontal, so we know horizontal is when your y prime is equal to 0, right? Anything dealing with horizontal tangent is the y prime. Anything with a vertical tangent is with x prime. So here's your strategy. You're trying to set y prime equal to 0. So build your y equation. Find the derivative, set that equal to 0. We go through product rules since we don't have f of theta to work with. Replace every theta with pi over 3, set equal to 0. Should match answer choice D. We're finishing up packet 2 from yesterday. Okay, 43. This is meant to be non-calculator here. A polar curve is given by r is equal to 10 theta over theta squared plus 1. What is the instantaneous rate of change of r with respect to theta when theta equals 2? So let's find dr over d theta. Once you find your dr d theta, replace every theta with 2. Number 44 feels like what we've done with second derivative or parametric. We gotta find d over d theta of dy dx divided by dx d theta. This one is calculator. Hey, let me know if you have any trouble with. Yeah. Always, we should always be in radian mode. Yeah. I don't think this course we're ever going to experience degree mode, so always radian. I would just still leave everything in rectangular form. I don't think that'd be in polar form for this. Yeah, just leave everything in rectangular form. I think polar form only if you're trying to graph something, I would say. Now, let me know if you're having trouble putting this in your calculator or getting that value to show up for you. Okay, page 21, 45. This is Riemann sums, but it's for polar graphs. So instead of multiplying width and heights, we're multiplying theta with r squared. So we know that each area of each of the sector regions is formed by 1/2 r squared theta. So our theta for each of our subinterval is by 1/4. So we can just do theta times r squared. And we want right Riemann sum, so that means we're going to pick the r value on the right side of each subinterval. 46, this is non-calculator. So you know that area formula is 1/2 integral from a to b of r squared d theta. So see if you can work your way through, get to your answer without a calculator. So use substitution, see if that will get you there. Actually, you may not need to use substitution because that square root and this r squared will cancel each other out. So I think power rule should be enough. Okay, 47. You can graph this. If you go to mode, yeah, this one you probably want to get into polar form. So click on mode, polar, graph it, and then you can trace it to see, how long does it take for that graph to finish. When I traced it, I was able to trace it all the way to 6.28, which is, we can indicate, no, that's going to be 2 pi. So really, it's just the area is from 0 to 2 pi, and then 1/2 r squared theta. Or 1/2 r squared d theta. For 48, find the area between the two curves. Just got to be careful understanding how polar graphs work. polar graphs work by, basically everything has to involve the origin. The origin is going to be involved with, we can't just say, oh, top curve minus bottom curve. We have to understand that if we want to find the area of this region, we have to first find the area of the entirety. Right? And then we can subtract out this portion, again, involving the polar zero. And then what remains is this outer portion. Just remember that anytime you're building your area, that it's always have to, all your sector regions is always involving the polar zero as it fans out. This one, we're just trying to get it into a cleaned up version of the integral. So we're not plugging in the calculator and getting some decimal value. We're just having to arrange it in a way that can allow us to simplify and see that it's matching amplitude. '49, same way, we find the area of the entirety of the outer larger area, larger region, and then we can subtract out that inner portion. Okay, any questions with 49? All right, 50. we have two graphs here. You have r equals 1.25 theta, and you have r is equal to cosine cubed 2 theta plus 1. If you graphed it, the r equals 2 cosine cubed 2 theta plus 1 is going to be this one here. And then your r is equal to 1.25 theta. It's going to be the one in green. We're trying to find the area of the shaded region here. So what is the area of the shaded region? It's nice they tell us that the two curves intersect at theta equals 0.8. So there's our intersection. And if we graphed it, we can see that this r equals cosine cubed 2 theta plus 1 starts here at theta equals 0, and it kind of moves in this direction. And at pi over 2, this will end up giving us cosine of pi, which is -1, -1 plus -1 is 0. It's going to hit that polar 0 at pi over 2 here. Meanwhile, this r equals 1.25 theta is starting at 0, and the region that we care about is right here. So we got to split this up into two areas here. So area is the 1/2 integral from 0 to 0.8 under the green graph, this 1.25 theta squared d theta. So this will give us this region here, right? This region up to that theta equals 0.8. So this piece here. This is what this is doing here. And then at 0.8, it's going to pick up and start hitting the other graph until it gets all the way to pi over 2. Okay, any questions? Page 23. Okay, let's move into packet 3. So this is going to be what your FRQ quiz Thursday after break will be coming from. There'll be two FRQs. You'll have a polar area FRQ, and then a second FRQ That is just a collection of potential miscellaneous BC topics. And then the second BC FRQ could be just any of these topics such as integration of parts, improper integrals, partial fraction, Euler's method, logistic model, arc length. So sometimes we just need to be familiar with these FRQs when they just have a random collection of these BC topics. So that is what your quiz the Thursday after you get back from break will look like. One polar area FRQ and one miscellaneous BC topic FRQ. Okay. Right, let's look at number one. Parts A, B, and C will just be your normal area. Yeah, your normal area area methods, either top minus bottom or right minus left that you learned with AB at the end of last semester. It's not until part C that we're dealing with polar regions. So parts A and B are just AB review, setting things up, setting up our area regions. Okay. So when it says with respect to X, that means get them into function form, get them into Y equals. And when it says with respect to Y, that means get them into a right minus left relationship. If we want to do top minus bottom with the x-axis, we have to split up into two separate regions. So we can do top minus bottom for this region, top minus bottom for this region, set up the bounds, and just set up your interval. Part B, we want to think in terms of, when we set it up, in terms of right minus left. So rewrite your equation in terms of x equals. That way we can set up adding infinitely thin rectangles that stacks this way instead of vertically. Part C is where we have to think in terms of, okay, I got to split this up here because there's going to be a change at power 4. That's where the intersection between the two graphs are. And I have to kind of think of it as splitting up my area into two separate regions because my sector are hitting different graphs at different points. So here's part C, understanding that we have to find the area of this region, and we got to find the area of this region. Because all these sector regions are hitting different curves from 0 to power 4. It's hitting the, we're hitting the circle centered at 0. And then from power 4 to power 2, we're hitting it, the other circle, the smaller circle, the 2 cosine theta. And we know that they intersect at power 4 because we can set the two curves equal to each other. So r equals √2 is a large circle, r equals 2 cosine theta is the smaller circle. Again, we're not doing much calculus here. We're just setting everything up. Okay, any questions? If you go to page 24 from the previous packet 2B, I just put some data here for you to look at in terms of, just kind of give you an idea how the AP exam kind of, especially BC exam, what their priority is in terms of topics covered. So you can tell that limits and continuity, it's a bigger deal on the AB exam. On the BC exam, they need to, prioritize other things. So, and it's the same length, so they're going to really cut down on limits and continuity. You see that the largest area that is going to be tested is going to be integration and accumulation of change. So a lot of integral problems. You're going to see that on the FRQs as well. And then parametric polar vector value function, that's 11%, and infinite sequence theory, that's almost 20%. So we definitely are going to be expecting a lot of this on the AP exam. Yeah.
So like the bigger percentages, like the integration and the infinite sequences, are there more of those, or are there like the same amount of questions, but they're more like they count more?
It's just a larger percentage of problems,
Okay.
but they don't necessarily count more. You just have more, potentially more of them. Yeah. And then also at the bottom, you can kind of see the percentage of grades of scores between AB and BC. I think it's just interesting to note that on the AB exam globally, it's spread out pretty evenly between 1 and 5s, around 20%. But you can tell that on BC exam, much higher rate for earning 4s and actually 5s, like almost 50% student get 5s, and very, very few students get 1s. So that's expected, right? BC students tend to have taken AB before, or they're coming in with better equipped. So Okay, so Monday, when we get back, we're gonna make progress with packet 3, but just know that the 2 weeks that we come back, we're doing a lot. We're quiz on Thursday, the following Tuesday, following Friday, we're going to have multiple choice tests. And then we can, we'll be done with in-class assessments by the 25th. Yeah. Okay. Let me answer your question individually so I can get students their phones. So yeah, come and get your phones. I'll come by and I'll answer your question.